Hello everybody and welcome to another video. In today's video I don't really have a clear objective or goal where this knowledge would be applicable to your code. It's just understanding and sharpening up our understanding of C++ and C at the same time. And this video is primarily and we'll use a lot of references of the video titled C++ Bypassing the Compiler Part 1. And you can say that this is the part 2 of this series, just because we're doing a lot of weird stuff in order to sharpen up our understanding of the language behind the scenes. Or rather, language behind the scenes and the code it generates and what's executed at runtime. So one of the first things here is that when we change, one moment. So one of the main points or key points in this video is that we get different runtime outputs or runtime responses once we execute our code at different optimization levels. And you would expect that that your optimization levels will not change your code execution at runtime, or the instructions that it needs to execute at runtime, to be exact. But that's not always the case. It will happen. It will happen in cases where you are doing a lot of weird stuff, a lot of unsafe stuff, where the compiler will have to be forced to fight with your bad code. And you really gotta give it to the guys who maintain and build and contribute to GCC for this kind of, for this level of intelligence from the compiler. So for example, what we did in the previous video titled C++ Bypassing the Compiler Part 1 is that we were getting the address of the temporary R value or X value or PTR value. It's all the same terminology. And we proved that is possible by printing out this reference object in the initializer or the constructor in the S class. And what I decided to name this function is aggressive, or address of aggressive, or you can call it aggressive address of. It would be more convenient to call it that. And this this should be commented out. So what we do there is we need to cast our const reference, and in that case the const pointer, into the normal pointer, because we wanted to move stuff out from, and we wanted to replicate the move semantics in the C++ 03 standard. So that's the context and the background of aggressive address of. Make sure to check out the previous video in order to get up to speed with it. So what I'm doing in this video is I want to point out and highlight how optimization levels can behave differently at different optimization levels, of course. So, and I'm doing really weird stuff in order to pull that off. And what I'm doing here is I'm trying to explicitly invoke my destructor of my class, and the destructor of my class will be checking for a null pointer in this case and cleaning up that data on heap. But as we talked about in previous videos, we don't really need that, because the implementation of the delete function itself does that for us, unless we overload it, which I'll get to in a moment. So it already does the null pointer check, but all we have to do is make sure to swap our existing pointer on heap holder or variable and swap it to null, and we will not run into that. But this should work if you think about it. The explicit destructor will clean up the contents of or the members of our struct or class, but at the same time it will again have to call the implicit destructor at the end of this scope lifetime. Or actually that would happen somewhere here before the return, if you want to be literal in that case. So that's when stuff gets interesting for different levels of optimizations. Because the compiler in C++, in this case G++, once it identifies that the destructor is called, it sort of marks that variable in that scope as used up. It's used. It cannot be used again. If it is used again, it is going to result in undefined behavior. Doesn't matter what your destructor logic is, whether you're swapping something you had on heap, or even your logic cannot get smarter than that. Just if my pointer is not null, I'm gonna free it up. Otherwise, I'm just gonna skip. So there's no more clear-cut logic than that. But what also compilers does is that now the state of that variable is done with. It's over. And now if you try to reuse it at some point, it will crash. But at O2 level optimizations, this is null, and we can validate that by assert dot iPointer equals to null, and in this case it will be null pointer because it's C++, and that's all good. However, the compiler will not look at it logically. It will try to do more work in terms of ensuring that there is no illegal stuff happening, such as calling multiple destructors at compile time, at runtime. So it will identify it, and even if I do O1 optimizations, it will be all fine. But stuff gets interesting when I do O2 optimizations. Now I'm calling double free. Give that a second. My internet is slow for some reason today. Alright. Yeah, so while that is compiling, even though, like I said, we swap that memory region or that memory address with the null pointer, still it's not enough for the compiler. That is because the compiler generates a lot of additional stuff when it comes to O2 and O3 level optimizations to ensure that your code is 100% sure, that is 100% safe to run, which means that is executed safely at runtime, in other words. So it will do a check here, where this check, we cannot find this one, right? And if you cannot find the label in your assembly output in the Compiler Explorer or similar assembly viewers or idles, you will have to include the library functions. And once I include the library functions, and this is to say, in other words, the standard library of C++, you can see now that we are checking for whether or not it's a bad cast or not. That's one check. The other check is, am I able to call the delete function? And another really wicked stuff that happens at these O2 levels is, I mean, it's really unpredictable. It can be when you're doing weird stuff like this. So I'm not seeing cleanup here, and I should be, because that's before I get to delete my pointer. So now if I use the standard output, it will be all fine. I will see the cleanup. That is because there is, it's sort of inexplicable, I have to say. You have to break down the assembly and what it does. At some point here, this C-type character moves what we need to print out in the RAX via print function. It sets it to an empty string. So while we are 100%, we are calling the puts function, which is the printf, it's still not printing anything because it's an empty string. Why does compiler do that? I don't know. I'm not sure. But if you wanna just write C++, you would prefer something standard that will work 100%, and you will not see weird things like this. But still, you know, it's very common to code C in C++. That's why there's a whole profession about not only C++ but C/C++ developers and engineers. So we can see, to get back to the initial point, when do I know, or how do we determine when is this exception message or error thrown? It's not the bad cast, and we can figure that out via reading the assembly output, and we can also figure that out by overriding the standard namespace function and throwing and printing out something of our own. So like I said, don't use printf, so I'll just replace that with stdcout, and we'll be all set. So it's not the bad cast that's being thrown, it's the double free that's being thrown. So eventually we get to the point where we call the operator delete. And it's really confusing, I guess, for beginners in C++ to understand that operator delete is just a function call. You know, it's not an operator. it's not like a binary arithmetic operator or basic arithmetic operators. It's just, or basic arithmetic operations. It's just a function call. The high level C++ developers will call it operator, because that's the word stock of a C++ dev. It is an operator if you look at your code at a high level, but essentially behind the scenes, and we talk about this a lot in the previous videos, where operator move assignment, operator move assignment, operator copy assignment, and copy constructor and move constructor, they're all just functions, but behind the scenes compiler sets them up. For example, move assignment and copy assignment, it makes sure that they're evaluated from right to left, but that's neither here nor there. The point is, it's all a function call. And once you break down your code, and once you get to the bottom of it and brass tacks of it, you will see that this call happens when I call my operator delete. And this delete, it's a keyword, but it's still a function call. We have to ensure to understand the difference between the two. I mean, there is no difference, just a function call. Keyword is a keyword, but it's different from an int declaration. This is to indicate to the compiler to put something into a certain register in order for us to store that variable. But this is a function call, and what we can do with function calls in C++, we can overload them. So how can we get to the bottom of this and figure out when this exception is actually called? It's obviously double free, and we know that it happens during the delete. So you can override your own function of the delete to verify that. And here we are not freeing anything because we don't want to raise any exceptions. However, now we left our, and also what I would like to say is, if you overload your own delete operator or delete function in this case, you can remove the overhead of the built-in delete that does the null pointer check. So now when you do the null pointer check, you are 100% positive that you're not doubling up the work. You're not calling the check twice. You're only calling it when you need it, and only when you need it. Not each time you call a delete, because each time you call a built-in delete, it will do a check for a null pointer, which is kind of bad if you are 100% sure that your null pointer is not that your pointer reference is not a null pointer. So if you want to build, let's say, if you want to micro optimize, you can write the operator delete, and in order to re-implement, you would but then you would need to implement your own malloc and stuff like that and copy, but that would be, yeah, it would scale up the work to unmanageable sort of scales. So one last thing here is we are not freeing our memory, and in order to check that, I will do the fsanitize, which I often use on all of the videos. Now we can see we detect memory leaks, but we are not detecting double free. That's because now, if we get to the bottom of it, we are not calling the built-in delete, which is gonna break our stuff. And I was using this before, and I didn't see my delete operator being deleted, and it wasn't even calling it, and I was really confused. But then I sort of realized, well, just read the assembly, and if you read the assembly, you will see that we are calling the one second, where is the operator? Operator delete. Oh, it's being inlined. So let me just comment this out. So if we look at the assembly code, we can see that we are calling the delete function under this function type signature or reference. So we have to make sure to override that one with size t. In this case, the compiler, the assembly output will see it as unsigned long, because for this machine, size t is unsigned long. So yeah. And just to wrap it up, we are not going to get these errors at O2 level, and because O2 level will not do all the checks. And last but not least, you never call your destructor like this explicitly. This is purely an experiment in order to improve our understanding of C++ and the compiler behavior. You would have a separate function that's called cleanup, and the way I'm just using that function is that I'm just reusing it in the destructor, so it does the same as the destructor. So I can just call cleanup, and it will not mess up with the compiler's mind, because the compiler, once it sees that there is a invocation of the destructor, it tries to generate smart code to detect all of the undefined and illegal behavior that we are breaking for the language, and this will work just fine. So always make sure you have a function that's already defined somewhere for that destructor, so that you can call it explicitly when you need to. Also make sure to check out the video C++ hacking destructor semantics part 1 and part 2, and optimizing move semantics and destructor semantics in C++ in order to understand and to have some context of what I'm talking about here. Okay, thank you very much for watching this video, and till next time, take care.